Most of the Gauss's law problems that we looked at in class dealt with Gauss's law for a conductor. Sometimes they will ask questions where they have a non-conductor. You have to be careful. You need to make sure you read the question carefully. So for example, in this question, they tell you that you have a non-conducting solid sphere. So the fact that it's non-conducting means that the charge is not just going to be on the surface. And in fact, they are very clear about that. They say that the charge is uniformly distributed throughout the volume. So it means that it has charge spread throughout the whole volume. So inside that sphere, there is an electric field because you do have some charge enclosed. And then, again, you have to be careful. The spherical shell that's around it is also a non-conducting spherical shell, and it has charge uniformly distributed throughout its volume also. So those are going to be key things that are going to allow you to go through and find the electric field in different regions. So the first thing that you're asked to do is you're asked to derive an expression for the electric field in different regions. So the first region that they ask for is within the solid sphere. And so again, you're going to need to use Gauss's law. This is going to be important. Because they say use Gauss's law and they say derive expressions, just writing down the answer is not going to be enough. You definitely need to make sure that you write down Gauss's law and that you use Gauss's law. So Gauss's law says that the electric flux, which is the integral of E dot dA, is going to have to equal Q enclosed over epsilon 0. Now for this, we're going to need to figure out what the enclosed charge is. So to do that, we have this sphere. It has a radius A, and it has a charge Q spread throughout it. And so its charge density is the charge per volume. So that's going to be Q divided by the volume of the sphere. So that's 4/3 pi times the radius A cubed. Now the enclosed charge is going to be the charge per volume times the volume of the Gaussian surface that we have. So when we're inside the sphere, we're going to have a sphere of radius r. Again, we want r is our variable. We're looking at the electric field as a function of r, and r is less than a. So in looking at this, the enclosed charge is going to be the charge per volume, Q over 4/3 pi a cubed, times the volume of the Gaussian sphere, which is 4/3 pi times the radius of the Gaussian sphere, r cubed. And this is going to simplify a little bit. You get the 4/3 to drop out, you get the pi to drop out, and so Q enclosed is going to be Q times r cubed over a cubed. So when we look at this, E is parallel to dA, and E is constant. So this integral over here becomes E times the surface area of the Gaussian sphere. Again, it's extremely important that you keep your Gaussian sphere and the non-conducting solid sphere straight. And so the flux that we're looking at is the flux through our Gaussian sphere. So that has a surface area. The surface area of a sphere is 4 pi r squared. So this has a surface area of 4 pi times the radius of the Gaussian sphere, which is r squared. And this is going to equal the enclosed charge, which is Q times r cubed over a cubed, divided by epsilon 0. So from here, it's just solving for the electric field. The electric field is going to equal q r cubed over a cubed epsilon 0, that's this term right here, also divided by 4 pi r squared. So this r squared cancels out two of these r's up here, which is going to be q over 4 pi epsilon 0 a cubed times r. This is something where the electric field is proportional to r, so it would be increasing like that. They don't ask you to draw that, but sometimes they will. So up until radius a, the electric field is increasing linearly. And then they ask you about the electric field between the solid sphere and the spherical shell. So that's in this white region right here. So that's between A and 2A. Well, when we look at this region, all we have enclosed is this entire spherical, um, this entire sphere, this entire solid sphere. So we have the total charge Q enclosed, and as we go out farther and farther in this region, we still are just enclosing the charge Q. So again, because they said derive these expressions, it is not okay to just write down the equation. You would need to actually write down the integral of E dot dA equals Q enclosed over epsilon 0. Say explicitly that the enclosed charge is Q, and then again, since you've already shown the work before, it'd be okay to just say E times 4 pi r squared equals Q over epsilon 0. So this is going to give the electric field is Q over 4 pi epsilon 0 r squared, which is just the electric field of a point charge. Again, we had the electric field was proportional to r when we were inside the solid sphere. It's just like a point charge where it's inversely proportional to r squared when we're outside of that point charge. For this next part, this part is a little bit trickier because we're looking at the electric field in that gray region. Um, so we need to go through, sorry, I shifted the page on myself. We need to go through and we're going to need to look at how much charge is enclosed. This is a non-conducting spherical shell, so we are going to have to figure out how much of the negative Q is enclosed. Not all of it is enclosed. It's going to be a similar idea that we did here, but the difference is the volume of the spherical shell is going to be slightly different. So as we go through to do this, the first thing I want to do is figure out the enclosed charge. So to figure out the enclosed charge, I need to first find the charge density. So as I go to calculate the charge density is, again, the charge per volume. So the charge here is negative Q, and the volume, this is where we have to be careful. We have a spherical shell, so if we look back at the drawing, the spherical shell has an inner radius of 2a and an outer radius of 3a. So this volume is 4/3 pi, and what we need is we need the total volume of this bigger sphere minus the volume of this smaller sphere. So it's 4/3 pi times 3a cubed minus 4/3 pi times 2a cubed. Again, this is just the volume of the outside sphere. This is the volume of the inside sphere. So this gives us a charge density of negative Q. We can simplify that a little bit because we have a 4/3 pi in both of the terms. So we have 4/3 pi times 3a cubed minus 2a cubed. Now again, you could simplify that a little bit more, but you know, we're not going to worry about that. You know, the 4/3 pi, or the 4/3 bringing out front, that'll be important. So when we go to find the enclosed charge, again, the enclosed charge is going to be rho times the volume. And our volume is the volume of this region right here in red. So my Gaussian sphere has a radius r. So this is going to be the charge density, which we had here, negative q over 4/3 pi times 3a cubed minus 2a cubed. And then my volume of that red region is 4/3 pi, and that's going to be r cubed minus 2a cubed. So again, with a little bit of simplifying, the 4/3 pi drops out. But instead of having a simpler expression like we had before, we have the ratio of r cubed minus 2a cubed over 3a cubed minus 2a cubed. Again, it's still the ratio, but we have to subtract off this inside hollow part. And so Gauss's law is going to tell us that E times 4 pi r squared is going to equal this whole enclosed charge. Again, it would be okay to start from this step right here, just because we had gone through and we had shown that in several steps. So I'm going to have 1 over epsilon 0 times my enclosed charge. So my enclosed charge is negative q, and then it's the ratio of r cubed minus 2a cubed over 3a cubed minus 2a cubed. There was one piece that I was forgetting here. This enclosed charge, what I was looking at was the charge on in this region right here. But the one thing that we have to be careful about, and I almost forgot this, we have to add in plus Q, because that's the charge that was sitting in this region right here, um, from this shell, or from this sphere. So again, we have to be careful when we're in this region right here. We have this little bit of charge enclosed in this shell, but we also have to add in the plus Q for this other charge. So the one piece that I need to quickly add is I just have to put a plus Q. Okay, and so then we need to solve for the electric field. And again, it's up to you on how much you want to simplify this. As you're trying to go through and do this quickly, I really wouldn't simplify a whole lot. Um, so we have 1 over 4 pi epsilon 0 r squared, and then we have this whole term right here, which is the plus q minus q times r cubed minus 2a cubed over 3a cubed minus 2a cubed. And again, that would be simplified enough. This shows that you knew how to find the enclosed charge, you knew how to handle the spherical shell, but again, it's still using the same idea of Gauss's law. Outside the spherical shell, you might think that that's going to be ugly, but when we're outside the shell, if we look, we had this inner sphere with a charge plus q, and we have this outer shell with a total charge of negative q. And so if we go to write down our enclosed charge, we have the charge on the inner sphere, which is plus q, and then we have the charge on the outside shell, which is negative q. So the total enclosed charge is 0. So E times 4 pi r squared equals 0. So the electric field equals 0. Okay. The next part asks for the electric potential at the outer surface of the spherical shell. At the surface where r equals 3a. And you need to then explain your reasoning. So for this part, they're asking for the voltage right at this edge right here. But the key thing is there's no electric field outside of this sphere. If there's no electric field outside of this sphere, then if I bring a charge from infinity all the way up to that edge of this sphere, I'm not doing any work against the electric field. Since the electric field is 0, the work done against the electric field is 0. It would not be enough to just say, since the electric field is 0, the voltage is 0. You would need to explain a little bit, at least in terms of an equation. But the absolute value of the change in voltage is the absolute value of the integral of E dot dr. And this is going from r equals infinity to r equals 3a. And for this part, this is where you could say, since the electric field is 0, this integral is going to be 0. And you could say see the integral, because then it's clear that you knew that it was integrating this 0, gives you 0 still. Um, the key thing is you have to explain the reasoning. So you wouldn't just be able to write down that the voltage is 0 since the electric field is 0 unless you actually showed the equation for this. Again, other ways of saying it are that there's no work needed to move a point charge since the electric field is 0. So the key is that the electric field was 0, but you need to explain why that works. The last part is derive an expression for the electric potential difference between points x and y in the figure. And so x is on the surface of this sphere, y is on the surface of the shell. It would have been much more difficult if they would have been, if you would have been needing to use the electric field in kind of this gray region right here. That was our really complicated electric field right here. But looking at the difference between x and y, we're looking at we need the electric field between this region, but that was just our point charge electric field. That was just this electric field equation. And so again, the magnitude of the voltage difference is the magnitude of the integral of E dot dr. This is going to be the absolute value of the integral from We're going to go from y to x. Doesn't matter if we go x to y or y to x. It's really going to be the same thing. Um, so, in fact, I should use the values of r for those. Um, so I'm actually going to go from x to y, but we'll look at this in a second. So I'm going to go from r equals, again, if I look back at this, it's r equals a to r equals 2a. And this was the integral of q over 4 pi epsilon 0 r squared dr, which, again, this is the equation for the voltage of a point charge. So this is the absolute value of q over 4 pi epsilon 0 r. Again, this integral would have been negative. There's several negative signs that are here. This is something where we're going to be able to figure out which of these points is at a higher voltage based on what direction the electric field points. And so the voltage difference, the magnitude of the voltage difference, is going to be q over 4 pi epsilon 0 times 1 over 2a minus 1 over a. And then they want to know, they didn't say find the magnitude of the voltage difference. They wanted to know the actual voltage difference. So if we look at this, the charge is positive right here. So our electric field is pointing from x to y in this region. And so that means that point y is at a lower voltage than x, because as you move in the direction of the electric field, the voltage decreases. So Vx is greater than Vy since the electric field decreases, since the voltage decreases. In the direction of the electric field. So this voltage difference is going to be positive. Now we have to look at this 1 over 2a minus 1 over a. This is 2 over 2a. So this is actually going to be q over 4 pi epsilon 0. We're going to have to do 1 over a minus 1 over 2a. Again, the reason is we needed a voltage that was positive, a voltage difference that was positive. If I left it in this order, 1 over 2a is smaller than 1 over a, and when I subtract this bigger number, I get something that's negative. So that is something that you would need to show. Just kind of quickly going through how you would have, how they would have broken down the points. For this problem, part A, part 1 of where it was the electric field inside the sphere, was worth 2 points. And so 1 point was for calculating the enclosed charge, and then 1 point was for the correct answer. But because it said derive this, if you just wrote down the answer, you didn't get any work. You needed to show this step right here, that E times 4 pi r squared equals the enclosed charge over epsilon 0. Again, you never know exactly how they're going to break down the points. So again, something showing that you're using Gauss's law was what you needed. But again, just writing down the answer would not have gotten you that point. For part 2, that was that region in between the sphere and the shell. And so it was 1 point for identifying that Q enclosed was Q, and then 1 point for the correct answer. But if you just said, oh, it's KQ over R squared, and you didn't explain why or show why, that would not have gotten you credit. So because it said derive, you should use Gauss's law to derive it. If you at least justified it with it acts just like a point charge in this region because your enclosed charge is Q, you probably would have gotten the credit, but it would not have been, you know, exactly what they were going for. Part 3, again, this was the part that was messy, but it was worth 4 points. That's because there were a lot more things to show. So recognizing that the enclosed charge is the sum of two charges, where we had, it's hard to read, but this is an equal sign. We had that charge Q from the inside shell, which is the part that I almost forgot, plus this other charge here. Again, they have that negative sign there because it was a negative charge. But showing that you knew that you had to add those things together was 1 point. It was 1 point for correctly calculating the charge enclosed by the shell, or correctly finding Q enclosed. Since a lot of people would have forgotten this charge right here, if you at least found the charge enclosed by the shell correctly, that would have been one of the points. And then 1 point, again, you need to show Gauss's law, so 1 point for doing E times 4 pi r squared, and then 1 point for correctly substituting in your enclosed charge from up here. So if you would have forgotten to include that Q, you could have gotten 3 out of the 4 points. And then part 4 was worth 2 points. 1 point was for correctly showing that the enclosed charge was 0, and then 1 point was for explaining, showing with Gauss's law that the electric field was 0. If you just wrote down that E equals 0, you didn't get any credit for that part. For the voltage difference, this was worth 3 points. For identifying that the voltage was 0 was 1 point, and then they said justify your answer. And so for the other 2 points, one way of saying it was saying that the integral, that the voltage difference is this integral, and since the electric field is 0, and the voltage at infinity is 0, that means that there's no change in voltage, and so the voltage is 0 at the surface. That's the way that we had said it. The other way is the other way that we had said it. The work done to bring a charge is 0, since the electric field is 0. Only 1 point of those 2 points is awarded if you just said that the total charge is 0 or that E equals 0. You could have gotten some credit, but that wouldn't have been a complete explanation. And then part C was worth 2 points. So it was 1 point for going through and doing this. Again, let V0 be the potential inside the outer sphere due to the charge on, you know, this was the method that we had used where we did our integral of this region in between. So I'm not going to look at this because this doesn't apply. We did the alternate solution. So the voltage difference between X and Y was this integral of this electric field, and we went from A to 2A. For setting up a correct integral with proper limits and signs, the limits could be switched if the integral had a positive sign. That's one of the reasons that I said just go ahead and do the absolute value, and then we explained why 1 point was at the higher voltage. So they have this positive voltage difference. We show that the voltage difference had to be positive. So this part right here would have been enough. You could have left it right at this step. But again, that was worth 2 points. Going through what they were asking for, the purpose of the question was to see if you understood how to use a spherically symmetric charge distribution, but not something that was a conductor. The average score for this one was 6 out of the 15, a little over 6 out of the 15. 22% of students got 12 or higher, but about 40% of students got 3 or below. Most students were able to do part A. Parts 2 and 4 were the most commonly correct because those end up being like the point charge. Part 3 was a definite challenge for many students, but that we said that was the hardest one. Most students got a majority of the points available for part B, and students also did generally well in part C. Again, I think that most of this question should have been fairly straightforward. Here's the part that I really wanted to show though. What were some common student errors or omissions? In part A, the question specifically asks students to derive their results using Gauss's law. If you just wrote down answers without showing it, you did not get any points. People also didn't know how to find the enclosed charge. But the most important thing is if it says derive your results using Gauss's law, you really need to show things. In Part B, students gave the correct answer that the voltage was 0, but the explanations were not always complete. In Part C, students used an integral, had difficulty setting the correct limits with the correct sign. That's why I always strongly recommend that you do the absolute value and then figure out which point is at a higher voltage. Um, so make sure that you understand keywords such as derive or show how you get your final answer. Um, and again, making sure that you know what type of response is expected makes sure that you're going to give them what they want. Um, if make sure that you know that you don't have to get a final reduced answer, you just have to set up an equation correctly. So again, this is something that takes a little bit of practice, but we have learned how to use Gauss's law, and this would help.